Good morning, everyone. We were talking about how to make salt pure. Last time we talked about having a field recrystallization, which can greatly improve the quality of the salt. And I think that we had also discussed, and you had mentioned that one of the problems is that if you have a recrystallization, then either you will require more land area or you will require more time. That is, of course, the negative thing about that. Let us see if there's any way to solve that problem. And this is something always come up with an idea. You yourself will know what are the positives and minuses of that idea. If it generally looks like a good idea, see if you can overcome the problems. Then nothing like it. If you can do that, that's wonderful. So let me show you. Like we discussed that if you produce salt, then you get a mother liquor, which is sea bittern, and that is highly concentrated in all salts. Most of the sodium chloride comes out, but after that, it is very rich in magnesium chloride, in magnesium sulfate, because these are soluble salts and they don't come out. Okay, so they will remain. Then there will be some uncrystallized sodium chloride, small buildup of potassium chloride, bromide salts, etc. And let me tell you, the magnesium chloride concentration can be as high as something like maybe around 200 grams per liter. That level of concentration could be even higher. Now, what is very interesting is that if you look at these are, of course, individual constituents, but sea bittern is, of course, a mixture of many salts. But if you look at the pure salts, and if you look at the osmotic pressure versus the concentration of these salts, we are talking about being somewhere in this region, somewhere here. Now, what you find is that, for example, if you see this green, what is green? Calcium chloride. This stuff is magnesium chloride. You can see that as you increase the concentration of these salts in water, which is exactly what happens in bittern, that there is such a rise in osmotic pressure. I'm sure most of you would not imagine this kind of osmotic pressures. Imagine if you had to generate this kind of pressure through mechanical energy. Even for something like seawater RO, where we use about 70 bar, and those pumps are very costly. So not to speak of when you have got this kind of pressures, and yet this is all just the pressure that is exerted by the osmotic pressure, and because it's a colligative property, osmotic pressure. So if you have got multiple constituents, they will all add up. Each one will contribute towards its osmotic pressure, and so the cumulative osmotic pressure can be quite high. And in fact, a calculation was done, and it comes out to around, I think, around 750 bar or in the vicinity of 700 bar for sea bitter. And that's available in your salt works. And most of it, the time, it's just being chucked back into the sea without doing any work. The second is, when we talked about doing recrystallization, you do recrystallization of what? Of sodium chloride. If I take a saturated sodium chloride solution, because that's what you will be recrystallizing from. Okay. Now that again has a osmotic pressure of something like 390 bar. And so, whereas seawater has an osmotic pressure of maybe around 26 bar, okay, thereabout. So there is a potential to suck out water from seawater using these things itself, the sea bittern and the saturated NaCl. So that's the kind of thing, because if I can suck it out, or at least some part of it, then I can reduce my land area requirement. So whatever I require for recrystallization, I might be able to offset by partly removing the water from seawater. So this is a membrane module. There are many of these hollow fibers. So this is all membrane. There are thousands of these packed inside a module. Now, what you can do is that you can pass seawater, let's say through the tube, through the inside of these fibers, and from the outside you can pass, let's say, sea bitter. So there is a huge osmotic gradient across this membrane, and because of that, you can get a dewatering. Of course, the volume of sea bittern is much lower than the volume of sea water. This may be what, just about 3% or 4% of this volume. But even so, because of its very high osmotic pressure, it has still an ability to squeeze out water. And so you can actually do this. You can demonstrate it actually by doing an experiment that something like maybe around 10% of the seawater can be dewatered by passing the sea bittern. And so, the whatever extra land, about 10% be required for doing recrystallization, you might be able to offset through this approach. And of course, there's always a downside to it. What the downside is really that you have to invest in capital. So it requires an equipment. You have to set up a plant, and you're talking about huge volumes. So the plant can be quite costly. So that would be the negative part, but technically it is feasible to do it. So just bear this in mind. Likewise, let me show you that as we are going to go into soda ash, and you have briefly talked about it, and we'll discuss in a little more detail about the soda ash process. Obviously, the most important requirement is that I have to make a saturated brine. I have to make a pure NaCl solution. And that's your feedstock on which you will be doing, let's say, the Solvay process. You don't do it with solid salt, you do it with a saturated brine. Now, what happens is usually we focus on the what we would call the feedstock, which is sodium chloride, and of course other things that you require like ammonia, etc., for the process. But people barely talk about water. In all these places where huge plants have been set up, like in Gujarat, millions of tons of soda ash is produced there. Now, what happens is that all these plants are along the coast. Naturally, because the salt is being produced along the coast, and so your soda ash plant is also set up in the vicinity of where salt is being produced. But there's no water there. In fact, there's a huge problem of fresh water availability in the coastal areas. And so all of these people typically have to set up their own seawater desalination plant, so that they can make fresh water. Because you cannot dissolve the salt in seawater. I mean, you can, but then there would be so much of impurity that the purification of the brine that you will have to do will make it a costly proposition. So nobody would do that. So you want good quality water. We'll also see what is the problem with all the other impurities that there are present in seawater and how those might interfere with your soda ash Solvay process. This is the example. You can see seawater RO plants are being installed by Nirma. It specifically says that when Nirma expanded their facility to include a new soda ash plant and a new power plant, they had an increased requirement for fresh water. So it clearly tells you, okay, that you need fresh water, and that fresh water is not available. Later on, we'll see that even if you do RO, it's quite an energy intensive process. And at the end of it, what are you doing? You're taking seawater, you're doing desalination, you're getting fresh water, and then you're putting dissolving the salt in the fresh water, and then you are making your brine. That's what you're doing. And the same with Tata Chemical. And in fact, they say that they were faced with the threat of actually having to close their plant. And so they had to also put up giant seawater plants. When I say giant, means we are talking about producing something like maybe 4 or 5 million liters of water every day. That's the kind of volume of these plants. They're huge. We'll see later on how to work out the energy requirement for these processes. The question I have for you is that from whatever I told you, is there a better alternative, let's say, to this, where I still am able to satisfy my end objective? End objective is to make a pure brine solution. So I've got pure salt. In both the cases, I've got pure salt. It's a question of the water. Can you see from whatever we have discussed, any possibility of coming up with a cheaper process to be able to still make pure brine, not dissolve the salt in the seawater, but to make a pure brine, but which would be more energy efficient than, let's say, doing RO?
Sir, ion exchange chromatography.
Yeah, you could do that. You mean you remove all the ions, right? That's what you're saying.
Yes, sir, kind of.
Yeah, you could. You'll have to just work out that is that a cheaper option or not. Let's assume, okay, that it is an attractive process. But don't forget that after I have absorbed these ions, I'll have to regenerate my column, right? I'll have to regenerate the resin.
Yes, sir.
Okay. And how do I regenerate resin? I have to add acid and alkali, right?
Yes, sir.
So you can see that there would be a huge requirement of acid and alkali. You yourself will be able to figure out whether it's going to be a viable solution or not. But I'll still put it down, ion exchange resins. Okay? And I'll put over here students. Okay, what else?
So precipitating out unwanted ions from
Wonderful.
seawater.
Wonderful, wonderful. 2. Precipitating out unwanted ions. Very nice. Which means that you will try and precipitate the calcium, the magnesium, etc. In fact, later on we'll see that before you actually start the Solvay process, there will always be small amounts of contaminants which will be present in the brine, and actually they are removed by precipitation. So what you are saying is correct. Only thing is that there we are talking about removing trace amounts, whereas here we might be talking about removing substantial amounts. Okay, like if you were to dissolve it in seawater. But yes, otherwise it's not a bad thought at all. Yeah. And of course, some things might be also difficult to precipitate out. Some things are easy, like magnesium, calcium, sulfate, carbonate. I should be able to take those out. But some of them might be a bit harder, like potassium or bromide, things like that, because they are soluble salts, more difficult to precipitate out. But good idea. Any others? Any other thoughts that come to your mind?
So, adding on to precipitation, we can convert them all to sulfates and then work it out. Convert all the anions into sulfates.
Well, you already have sulfate in seawater, for example. Convert to sulfate, but sometimes I've seen that sometimes you may suggest something and it may at that point look like no, it's not such a good idea, but later on you might find a variation of what you're saying, and that could be a good idea. That's why I never neglect these things. There could be some interesting ideas. I don't know. Okay. Anything else?
So pressurize the water till the extent that the salt precipitates out and then mix it with water.
Pressurize. Oh,
Yes, sir.
why do salts precipitate out with pressurization?
So because now for the same volume, sir, the liquid has a lot less space. So the salt,
But no, wait a second. But liquids are not compressible.
no, sir.
Then
But
how is
still
it
we can
possible
apply
to say?
pressure on the liquid as a whole, sir. Like
No, but you can apply pressure. It will just flow somewhere else. But it's not going to change its volume by getting
so
compressed.
in a container, sir, in a container we have to apply pressure.
Yeah, even if you apply pressure, okay. I mean, a liquid is incompressible,
Okay, sir.
isn't it? Huh? Your airspace will get pressurized, okay. But and what will happen is that air space will the pressure will exert a pressure on the liquid, okay. That is like pneumatic pressure, and then what will happen is that it will do one of two things. If there is any place for it to flow out, it will flow out, or if the reactor or vessel cannot take that pressure, it can burst. But as such, a liquid does not get compressed. Your idea was good. If it was a gas, probably it would have been better.
Okay, sir.
Okay, huh?
Thank you.
To reduce volume and hence precipitate. Incompressible. Okay, so you'll understand what I'm saying. Anything else?
Sir, decrease the temperature.
Yeah, very interesting. But then you know that there is an energy input, right?
Yes, sir.
You could also think of that way. You could even think of salting out. If you add some solvent, it will lower the solubility of these things, and things can precipitate out. And after that, you can strip off the solvent. But then you'll have to look at the energy input. Okay, huh? And I'm just putting also that salting out because you would have probably learned it. But in all of these things, what you have to look at is the whatever is the most practical suggestion. To me, it seems, I mean, I might be wrong, but to me, it seems that getting fresh water by RO would probably be cheaper than doing any of this. You understand what I'm saying? So, in which case, people will do RO. They're not going to do all this. And also, RO is a very non-selective technique. So, it removes everything at one go. The membrane is such that it only allows the water to permeate and everything else stays behind. So, I don't have to worry whether X will precipitate or Y will precipitate. There's no such worry. Everything will get out. But even RO is a fairly energy intensive technique. So let me show you another option. Now, and it follows on from whatever I told you about the osmotic pressure. So I told you about forward osmosis. Let's say this is seawater. Its osmotic pressure is about 26 bar. This is saturated brine, about 392 bar. Now, what will happen is obviously water will flow from here to here in that kind of a module that I told you, and it's a spontaneous process. Whereas reverse osmosis, etc., is a non-spontaneous process. That's why you require energy. This is a spontaneous process. I only need to circulate these feed and draw, and other than that, the water will get removed on its own by a spontaneous process. But then once it pulls in water, it is no longer saturated because naturally water has gone in. But then for the Solvay process, you need saturated brine. So what you can do is that you can add more sodium chloride because it's undersaturated. So effectively, what will happen is that I can again remake a saturated brine. The only difference is that suppose here I had X liters and here I will end up getting Y liters where Y is more than X. And so what I can do is that I can recycle X liter into my system so that I continue with this process, and y minus x will be my surplus, which can just go for the Solvay process. Now, what are the assumptions? The assumption is that only pure water permeates across the membrane, just like in RO. And in fact, it is true. None of these other things present in seawater will cross over. Only the pure water gets transported. So in the process, what have you done? Like, let's say if the original way of doing it, what all these guys are practicing is this, that you first do RO, you get fresh water, then you dissolve the salt in your fresh water and you make saturated brine. So effectively, you ended up doing the same thing, except that now you have done it by a spontaneous process rather than through a non-spontaneous process. Is it clear to everyone?
So why did the saturated brine turn into unsaturated brine?
Because I'm getting water in.
So, but you've obtained the saturated brine from the seawater, right? So,
No. This is the saturated brine which I'm making by, let's say, taking my salt and I'm dissolving it initially in a small amount of water. That water you'll have to do, but that's only for initiating the process. So I've made a saturated brine from solid NaCl and a small amount of water, and the rest of it is the water is getting pulled in from the seawater. So now naturally, if I've got say 36% sodium chloride as the saturation point, once it draws in water, it will no longer be 36% because only the water is going through and not the salts. So I now have made it undersaturated, so it has got the capacity to absorb more salt. Is that clear?
yes, sir.
Always there is an opportunity to look in a clever way. In fact, let me tell you, this year, one of the students who graduated this year, Merul Shah, okay, he actually did a home paper where I had asked him to do all the calculations of energy, etc., for that kind of a process compared to doing RO. He had done that. He was one of the contestants in what is known as the Innovative Students Project Award, given at the bachelor's level in India across all branches. It's not just chemical engineering, any branch. And they give about, I think, about 8 awards at a maximum. And he is the recipient of this year's award. You can see Innovative Student Projects Award, and it's actually this award is really constituted by the Indian National Academy of Engineering. So this is the highest engineering body in our country. And you can see what it says. Design a brine preparation unit to manufacture 2000 tons per day of soda ash using seawater as raw material. But not doing RO, but where you are doing that kind of thing. Recently, this invention has also been granted a patent. So there is always room. And in fact, what you should do is that when you are taking all these courses and things, try to create opportunities for yourself where you might be able to do some project or internship or something. So always look at it that way. Don't just look at it as a topic and a course and things like that. Always look for opportunities. Now, in fact, since one of you said it's very nice, you mentioned that you can precipitate out things. And that's exactly what you do. I showed you that you can make something like 98-99% purity salt. I mean, I'm not even talking about with recrystallization. I'm just talking about, let's say, through a salt washery, which the majority of people will do. These are new technologies. Maybe 10 years down the line, they will get implemented. As of now, nobody would practice whatever I told you just now. Okay. So there will always be some impurities. And secondly, even if you do RO, it doesn't give you distilled water. There will always be some impurities, okay, which will be left over from the seawater, though 99.9% would be removed, but that 0.1% might stay. And so this is one way in which brines are purified. Exactly, I mean, I think some of you had the right idea, which is interesting. So what you have to do is that you have to look for which are the least soluble compound which can be precipitated. Now, for example, if I have calcium and magnesium in seawater, okay, we know it's present. Okay, although most of the calcium comes out by the time you come to gypsum, but still we found that some amount of calcium, etc., remains in the salt. Now I can add an alkali. What will happen is that magnesium hydroxide has extremely low solubility, so it will precipitate. But calcium hydroxide is sparingly soluble because you can make slaked lime and things like that. So you're not going to be able to remove the calcium as calcium hydroxide, although the magnesium you might be able to remove. Okay. Now, what you may do is that you remove the magnesium that way as hydroxide, and later on what you can do is that you can then treat it with sodium carbonate because calcium carbonate is highly insoluble. And if you have got traces of any magnesium which is left over, then that also can precipitate out. This is known as a lime soda treatment, which is one way of removing traces of impurities. Later on, we come to the chloralkali. Oh, it's unbelievable. At what level of purity you have to prepare brine. Levels of purification that you require are much less stringent for soda ash. But I think you've got an idea, and it's in sync with what you all are were proposing. But only thing, remember that you have to have chemicals which are added, and chemicals will add to cost. You can only remove them by this kind of a method only if they're present in traces, not otherwise. So you could actually do a precipitation. Is that clear? Everybody understood?
Yes, sir.
Okay. So now let us look at the actual Solvay process. Like we talked about the contact process, it's such a landmark process. We need to cover it in some detail. What are the inputs we have? We have limestone, we have sodium chloride, and we have ammonia. And then, a small amount of some of these compounds that we talked about to purify the brine, small requirements of that. And what did we say? That Solvay process is one of those where you can look at it as a coupled reaction, where you are overcoming the non-spontaneous nature of the Solvay process by giving an energy input in one of the operations, and that operation is really that you calcine limestone and you will form calcium oxide plus carbon dioxide, and that of course requires an input of energy because it's a non-spontaneous process. And then what did we say? That you need purified brine. This is a lime kiln. So this is from where you will be putting in calcium carbonate, and then there will be a heat supply from somewhere here, and then in this kiln the limestone will decompose and form carbon dioxide and calcium oxide quicklime. Of course, you need an energy input for that. What you'll do is you'll add some coke, which can get converted into carbon dioxide, and in the process you'll generate the temperatures at which you can effect the decomposition of calcium carbonate. What else do you require? You require air, because after all the coke has to get converted into CO2. That's the process of combustion, and so that will require air. So you'll have to put in air. Okay? So that's what you require in the lime kiln. And then what will you get out? Because I have put in air. So air is, as we know, 80% is nitrogen, and of course most of the oxygen will get consumed in the combustion process. Okay, but still, and it will form CO2. But that CO2 because it's going to be mostly diluted with nitrogen. Because I fed air, I did not feed pure oxygen. If I fed pure oxygen, of course, you would have got a very concentrated CO2. But here I am feeding air, so it will be a lean flue gas. Okay? So this is my flue gas. It will be mostly CO2 plus nitrogen, plus of course traces of other things which will be present. And then from the bottom I take out the lime. Where does the lime go in the Solvay process? What is it used for?
So eliminate any HCl which is there or any absorb water, I guess.
No. Any other? Well, the lime is what will be used to regenerate the ammonia. It is the regeneration from ammonium chloride. We'll go through the process, and that's part of the Solvay process. That's what you require the lime for. And it will also form calcium chloride as a byproduct. And then you add water, you have a slaking device, and so you end up forming milk of lime, calcium hydroxide. And this is what will be used for making the Solvay process catalytic in ammonia. You don't consume ammonia actually in the process. And then what you have is that you have an ammoniation tower. So you're feeding sodium chloride and you're bubbling ammonia. Why? Because the Solvay process is all about effectively converting sodium chloride into sodium bicarbonate. It is happening via ammonium carbonate. That is the brilliance of the Solvay process. And that's why you need ammonia. Okay? So it becomes an ammoniated brine. Okay? And then what will happen is that my ammonia and NaCl solution will go into the Solvay carbonation tower. So the Solvay process has two separate towers. One is the ammonia tower, which I'm showing you, and the next will be the carbonation tower. Now there are reasons why two separate towers have been kept. I could have actually in principle mixed it all up. I mean, I pass ammonia, I pass CO2, I take NaCl, everything in one tower, and I do my reaction. It's not impossible, I can do it, but this is a preferred thing. Can anyone anticipate what may be the advantage of doing it separately? And let me also ask you the question that instead of first passing ammonia into the brine, what would happen if I passed CO2 into this brine and then I passed it into an ammoniation tower? So if I had put my carbonation tower first and then put my ammoniation tower, I could have done that, but obviously that wouldn't make sense. Can anyone offer any suggestions on either of these questions? Why it is done this way?
So carbonation is done later because
Yeah.
if carbonation was done earlier, then the ammonia would react with the ammonia would react like to form ammonium carbonate rather.
Yeah, but you want it to, that's exactly what will form. Ammonium carbonate is the intermediate in the Solvay process. And that's precisely what will happen in my next tower. But the problem is, you see, ammonia has relatively high solubility in brine. So I can feed it in. Whereas CO2 has extremely limited solubility in brine. So I really cannot put the CO2 unless I have a high pressure, which I am exerting. Otherwise, you've got such a limited solubility of CO2 that the reverse sequence would never be useful. Okay? The second reason, and you'll find out as I go along, is that the temperature profile in this whole process is very, very critical. Because I have to finally precipitate out something, I need to have a low temperature at the point when things are being precipitated out. Now, let me ask you, when I add ammonia into brine, will there be any exothermicity or endothermicity of this process of dissolution? Will it absorb heat or liberate heat or do nothing?
So absorb heat.
Absorb. So it will be endothermic?
Yes, sir.
So ammonia absorption would be exothermic, but
Yes.
CO2 absorption would be endothermic.
Yeah. So ammonia absorption is exothermic. And so what happens is that in the next stage, again, I'll have to do cooling and things like that in this tower. So the best thing is that if some heat is being evolved, the best thing is to remove that heat prior to putting the ammoniated brine into the carbonation tower. So that's what you'll do. And this is the heat exchanger. So there is a buildup of heat and you have a heat exchanger. So you're cooling it down more or less to room temperature and then you are feeding it in. And even this temperature is not acceptable. You need to go down still lower in temperature. So you do a further cooling in this tower. Now, this is, as I told you, what really Solvay became famous for. Solvay did not invent the Solvay process. I told you there's an earlier patent and Fresnel had effectively discovered this reaction, the core reaction in the Solvay process. So there was nothing in terms of the chemistry that Solvay really added to, virtually nothing. But he and his company did a great job of the engineering of this whole process, and that's what made it successful. And these towers, they're very tall. You can see about 25 meters. So you're talking about 75 feet, that kind of a height. And look at the diameter also. Something like 6 to 8 feet in diameter, and made of cast iron. So it's giant. These towers. So what are we doing? You're dropping the saturated brine with ammonia saturation into this tower, and we'll see what else is happening there. What else do we require? We require carbon dioxide. Now this is a lean stream of carbon dioxide, so this is not this stream, and I'll show you where this stream is going. And this is a rich stream of CO2, and I'll show you where this rich stream of CO2 is coming from. And this cooling water, so that even 30 degrees centigrade is not acceptable, and so you need to cool it down to 20 to 25 degrees centigrade. Over here the temperature is rising and then there is a cooling here. Can anyone tell me why the temperature rises? Why does the temperature rise?
Dissolution of ammonia.
No, solution of ammonia to idhar ho gaya. I have now got it, I have put it here, and I am putting carbon dioxide from here. I am asking you why the temperature rises.
So we are heating it, right?
No, you are not heating it.
Sir, reaction was exothermic between
Yes.
H4H and CO2.
Yes, that's all. Okay, absolutely. Ammonium carbonate formation is exothermic. Okay, that's all. So just remember that if carbon dioxide is coming from the bottom and my ammonia is coming from the top, the most likely place where maximum reaction will take place and the concentrations of both would be optimized would be somewhere here. So it will be somewhere in the middle of the of that reactor. And once it heats up, and later on I have to collect something, I have to get a solid out. So again I need a heat exchange, okay, so that I can cool it down. So this is a heat exchanger, whereas this temperature rise is purely because of the exothermicity of the reaction. Now, what am I forming? I'm actually forming first, I've got ammonia, and that ammonia is reacting with carbon dioxide, and it is, now let me ask you, if I have to look at the pH profile along this tower, okay, from the top to the bottom, where would the pH be highest?
At the topmost point?
Yeah, at the top. And where would the pH be the lowest?
Bottommost?
Bottommost. Absolutely. Because carbon dioxide is acidic. So here I am putting the carbon dioxide from here. And over here, what will happen is that it will in between. These are the two extremities of pH. So naturally the pH in between will be also in between the two extremes of pH. So when carbon dioxide reacts and at the top of the tower, what are you most likely to get when ammonia and carbon dioxide react? Which species would be formed?
Carbonate, ammonium carbonate.
Brilliant! Ammonium carbonate. And towards the bottom, what are you more likely to form?
Bicarbonate.
Absolutely. Ammonium bicarbonate will form nearer to the bottom and ammonium carbonate will form nearer to the top. So you can see that there will be a crossover as the brine with ammonia is traveling down. There will be a crossover from ammonium carbonate to ammonium bicarbonate. What did we then say? You remember I had shown you the solubilities of sodium bicarbonate, sodium carbonate, sodium chloride. Now what happens is this is at the heart of the Solvay process. That for whatever reason, sodium bicarbonate has the lowest solubility. So even if I form ammonium bicarbonate and I've got sodium chloride here, I've put in sodium chloride. So the sodium chloride will react with my ammonium bicarbonate, okay, towards the middle to the bottom, and it will form sodium bicarbonate and precipitate out. Why? And that's why you need to cool, so that you know the solubility of sodium bicarbonate is the least among all of these. So that will be the thing that will precipitate out. Okay, and so that's effectively what is happening. Sodium chloride and ammonia are going in. Carbon dioxide is going up. It will initially form ammonium carbonate. Nothing will happen with sodium chloride because sodium carbonate is also very soluble. When it starts coming down and it sees more and more of carbon dioxide, then it will from ammonium bicarbonate it will become ammonium bicarbonate. Now there will be a cross reaction between sodium chloride and ammonium bicarbonate driven by the low solubility of sodium bicarbonate. And so that is what will precipitate out, and I'll be left in solution with ammonium chloride. The chloride coming from the sodium chloride and the ammonium coming from the ammonium bicarbonate. So I have got ammonium chloride in solution. Now you'll also find that it is not pure ammonium chloride. There will be some amount of sodium chloride because this reaction is not 100%. We'll see that it's nowhere near 100%. So there will be a lot of unreacted sodium chloride which will also be dissolved in over here. And this is the solid, and this ammonium chloride will be in the mother liquor. What will happen is that then you take it through a rotary filter and you separate the solid, which will be my sodium bicarbonate. Then what you do is that this is a rotary calciner. So what happens is that this sodium bicarbonate, you need to convert it into soda ash because soda ash is sodium carbonate. So what happens is that when I heat up sodium bicarbonate to a temperature of around 200 degrees centigrade, then the two NaHCO3 will basically become Na2CO3 and it will release water and 1 mole of CO2. So sodium bicarbonate decomposes to sodium carbonate plus CO2 plus water. And this is done by heating up. So I can either take pressurized steam or I can take something like coke and air and burn it and generate the heat. Now in this particular case, what you do is that it's like a reverberatory rotary calciner, that is it's jacketed, and you you generate the heat on the outside so that whatever CO2 comes out will be a pure CO2, because now there's no air which is getting mixed up here. Okay. Second, let me tell you, and this is all part of engineering ingenuity, that when even though it's rotary, as the sodium carbonate is being formed, what happens is that a lot of the sodium carbonate goes and sticks to the sides of this calciner, and because of that the heat transfer efficiency reduces. So what they do is that they have heavy scrapers, and it continuously keeps scraping out any solid that is sticking to the sides of this calciner. So it gets scraped out, and so that you maintain a clean surface, so that you can have good heat transfer efficiency. Another way in which you can reduce the amount of this encrustation of sodium carbonate on the sides is that they found that because the cake is wet, and hence there is a tendency for it to stick to the surfaces, that tendency is more. But once I add some solid sodium carbonate, which is dry stuff, dry sodium carbonate, I mix some of the wet with the dry product, and because the overall thing becomes more free flowing and it has much less tendency to stick on the surface. I hope you can understand the difference between chemistry, chemical equations, and engineering solutions. Okay, and that's what you should focus on as much on as the chemistry. Whenever you get into this kind of problem, see how you can innovatively solve the problem. So what is happening is that during the decomposition, when sodium carbonate is being formed, I told you that CO2 will come out. There will also be, when I do this filtration, there will always be small amount of unreacted ammonia plus the ammonium chloride, which maybe remains as a adhering liquid in my solid. Those also will be all there in this stuff. So when I'm heating it, the ammonium chloride will also decompose and release ammonia, and it will also come out along with my CO2, etc. So that's all coming out from the calciner. From the other side, what I'm getting is I'm getting hot sodium carbonate, and that hot sodium carbonate is cooled by spraying water, not in my solid, because my solid is solid. I don't want to do anything with it. I mean, it's just flowing from the outside of the vessel. And that's what is known as the light soda ash. And why? Because when you are doing this calcination, some amount of CO2 tends to get trapped in my sodium carbonate, and so it reduces the overall density of the product. So you get light soda ash, and then one has to do a separate process to convert it into heavy soda ash wherever it's required. So I've taken this out. Now what happens is that I also have ammonium chloride from here, which basically comes out as my filtrate. This CO2, which you see, which came out, because the flue gas in this particular case did not have any nitrogen, because it was indirectly heated. So it's coming out hot. I do a heat exchange, and then this is the rich CO2 which I'm taking. That because it's all pure CO2, and whatever moisture etc. came out, it will get absorbed here in this solution, and so I only have CO2 coming out from here. So that is my rich CO2 stream, and whatever ammonia etc. Came out, that along with the ammonium chloride. So this is my stream, which has partly ammonia, partly ammonium chloride. So effectively, this is the one that will be treated with the lime. First, you'll strip off the free ammonia. After that, you'll react it with lime and release ammonia. But before you do that, there is also a lean stream of flue gas, which is this, okay? And this stuff is now being fed into the middle of the reactor. So it's very interesting. I've got more ammonia here. I've got very little ammonia here, okay, and also very little sodium chloride because most of it would have reacted. But I've got a lot of CO2. Here I've got very little of one of the reactants. Here I've got very little of one of the reactants. And in the middle, because both of them will have reasonable concentration, the ammonia and the CO2. So it is much better that I put the lean CO2 here, rather than putting the rich CO2 here and the lean CO2 here. Because this is the place where I want the pH to be right for maximum formation of sodium bicarbonate. So that's what I do. After the reaction is over, there will always be some amount of gases which did not react, and that will be some of the CO2 from this lean CO2 plus the nitrogen, plus if there are traces of ammonia, etc., which didn't react, some of it will get absorbed and some of it might come out in the gases. Those are being fed back into this ammoniation tower, and from there it is being allowed to exit. And because there will be traces of ammonia, I can use ammonia for purification of brine. So instead of adding sodium hydroxide, I might as well add ammonium hydroxide to precipitate out magnesium hydroxide. So that's the best use of whatever traces of ammonia is coming out. This is my still, okay, which is my free ammonia still. So what I do is I heat it up. So whatever is free ammonia, it just comes out. And once the free ammonia has come out, the rest of the ammonium chloride I take into a second still. Okay, so this is bound ammonia in the form of ammonium chloride, and when I add lime to it, because lime is a stronger base, so it will basically end up forming ammonium chloride will get converted into calcium chloride and free ammonia. So I'll get some ammonia coming out from here and some ammonia coming out from here. And this is my calcium chloride waste. So Solvay process is not such a great process. It generates a huge amount of effluent. And it's not just CaCl2. Whatever unreacted sodium chloride was here, because the reaction is not 100%, that will also contaminate the calcium chloride. So it's not pure calcium chloride. It's basically calcium chloride, sodium chloride. Both the ammonia that came out from here, that I'm just putting back into my ammoniation tower. And of course, there will be traces of losses. I'll never get back all of the ammonia. Tiny amount is lost, so I'll have to top it up. So small amount of ammonia I may need to put in from outside, but the majority is basically recycled, and it's all possible because of the lime. And why did I need the lime? I needed it because I also needed CO2. So I'm getting the CO2 over here, and the lime is now being utilized to release my ammonia. So is that clear? What is the process? So this is my makeup ammonia. By the way, the limestone calcination requires about 1000 degrees centigrade temperature. So it's a fairly high temperature process. So that is effectively the Solvay process. Has everybody understood the process?
So I had a small doubt, sir.
Yeah.
So why did we do the indirect heating and how did it help in eliminating the nitrogen?
Yeah, over here.
Yes, sir.
See, I need a rich source of CO2, carbon dioxide. My decomposition of sodium bicarbonate to form sodium carbonate. If I take 2 sodium bicarbonate, there's 2 carbonates, right? And at the end, when it becomes Na2Cl3, I've got 1 carbonate. So the other one was released as CO2. Now, if I do an indirect heating of this, one is that I will make a pure product. There will be no contamination coming from anywhere. And secondly, because there's nothing else, the only gaseous substance that is coming out is my CO2. And traces of ammonia plus moisture, etc., which will all get absorbed in this aqueous phase. Okay, and so finally what will come out, in the gas phase here will be just CO2, which will be a rich source of CO2. Is that clear now?
Yes, sir. Thank you, sir.
Okay, just to show you the finer details of some of the equipment, the lime kiln, where we said that you are calcining calcium carbonate and converting it into lime and carbon dioxide. Usually these lime kilns are vertical kilns, very, very tall kilns, and this limestone is not in a powdered form. They're like boulders. You can see, because that's the way you will bring in limestone. They'll be like rocks. That is what you are feeding, those literally boulders on the top. This is the point at which you are introducing the fuel. So this is where really your decomposition is taking place, because this is the hottest zone. You have to control the residence time, very, very subtly, and that you do by deciding what will be the rate of discharge of the calcium oxide which is coming out after you have done your calcination. Because if I can control it here, then obviously the amount that I can feed here will accordingly get controlled as well. And because it's coming out very hot, so you have to cool it. That's done with the help of cooling air. From here is coming out that lean gas, which we talked about. Okay, the CO2 with nitrogen. That's what is going into the middle of your Solvay carbonation tower. There's another reason why you need to control this time and also the temperature, because if it is too high, the temperature, then what can happen is that the calcium oxide can get sintered. So you must prevent the sintering. That's one. And secondly, you have to also at the same time ensure that all of the calcium carbonate is completely converted into calcium oxide plus CO2. Because if it comes out of here and most of it is still calcium carbonate, it's no use. So this is how the vertical shaft kiln operates. It's also got fairly good efficiency. If you look at the decomposition temperature, it comes to about 3010 kilojoule per kg of calcium oxide, and the overall efficiency that you get is something like 4000 kilojoule per kg, which is not bad. In other words, you're operating this at about 75% efficiency, the heat transfer efficiency, which is really very good. As far as the rotary kiln is concerned, rotary kilns are used typically whenever I've got powdery material. Whatever sodium bicarbonate was formed in the Solvay carbonation tower, that's all powder. It's just a precipitate. So that is fed into this rotary calciner, and the calciner basically rotates so that nothing sticks to the surface, or you minimize that sticking, and also that way you maximize the uniformity of heating of all of the powder which you do over here. And the things that I told you about the mixing of the wet mass with the dry sodium carbonate and use of scrapers. Now in this, partly because it's also an indirect heating, the energy requirement is a lot higher. What we will see now is, let's just break it up. We saw that you have got what is known as a making tower, and that's where you are actually making the sodium bicarbonate via ammonium carbonate, which then went to ammonium bicarbonate, which then did a cross reaction, and you formed sodium bicarbonate, which came out because it had the lowest solubility. That's effectively what you're doing. Now, we have also looked at the calcination, the kilns. We've also looked at the ammonia recovery system, which is extremely important. You can see that so good is the ammonia recovery process that your ammonia loss is just 1 kg per ton of sodium carbonate. Can you believe that? It is just unbelievable how good the recovery is. And then you've got a fourth issue, which is that this calcium chloride and sodium chloride liquor that comes out, that is the waste. Okay? That what do you do with it? In fact, let me tell you, in many places, the Solvay plants had to be shut down because they could not find a suitable way of dealing with this waste. Many places in the world, the Solvay plants had to shut down because of this problem. In our country, it goes on because they are all along the coast, and of course, one needs to be very careful how it is discharged. But I'll also show you some applications. You know that the Solvay process is a continuous process. The way it is made continuous, just like we saw in when we were looking at the Klaus process, is that you don't have only one tower. You have something like 6 towers, 6 of these, and at any given time, 5 of them will be in operation, and the 6th will be basically in a cleaning mode. It's being cleaned, and so by rotation, all of them will at some point be on the sidelines, basically being cleaned up. Okay, but the rest of them will be operating. That's the only way in which I can maintain a continuous process. If I had only one reactor, I can't have a continuous process, because after some time, what happens is, just like I showed you in the case of the rotary calciner and how things can go and sit on the sides. Similarly here, when you form sodium bicarbonate, well, ideally all of it should really come out, and then you filter it, but it never happens. Some amount will always stick to the sides. Secondly, I didn't show you how the inside of these carbonation towers look. Remember, it is a gas liquid reaction. CO2 is in the gas phase. It has to react with ammonia in the liquid phase. And so you will have to have very intimate contact between the gas and the liquid. And the best way of achieving that is by maximizing the liquid surface area, so that the CO2 will see a thin film of the liquid rather than a bulk solution. So what happens is that when the ammoniated brine is being dropped, these are like packings which are almost like mushroom shape, and so it is just falling on it, and it's going from the sides, and these are somewhat porous, these packings, and so the CO2 is actually going through those pores also, and there is a very intimate mixing that takes place between the liquid and the gas, and that is what is giving you a very good reaction rate. And if you did not have that, your reaction would be very slow. So one is the height of the tower, which is critical, and the second is the design of the inside of the tower, which allows for a maximum interface between the gas and the liquid. What formed sodium bicarbonate? Why did sodium bicarbonate form? Because it is the least soluble, and that's why it precipitated out. Okay, but the same thing which I'm filtering and getting out, part of it is sticking to my reactor. So I need to make sure that none of my sodium bicarbonate is remaining in the tower after I've done the cleaning job. What would be the best way of doing that? What would I do to clean it up? And think solubility. Is there any way I can solve the problem? See, I've given you the hint that sodium bicarbonate is solid, and that's the reason why it sticks. So what I do is that now I reverse the process. Means try to go back from sodium bicarbonate to ammonium carbonate, because ammonium carbonate and even ammonium bicarbonate has got a much higher solubility than sodium bicarbonate, and ammonium carbonate has got still higher solubility than the ammonium bicarbonate. And the beauty is that sodium chloride, as we had seen, there is no change in the solubility with temperature. Okay, I mean, these are of course shown at 3 different temperatures, but you can see that suppose I take 20 degrees centigrade as my temperature, or 30, you can see how much is the solubility of sodium bicarbonate, how much is for ammonium chloride, for ammonium bicarbonate, and for sodium chloride. In my reactor, most of my sodium chloride has already reacted. Only about maybe 20-30% is unreacted. Most of my ammonia would have reacted. So what I do is that from the ammoniation tower, I don't put in the that ammoniated brine directly into the tower during the making phase. What I do is that the one that I've isolated for cleaning, I put my ammoniated brine here. So what will now happen is that the sodium bicarbonate, in presence of my high amount of ammonia which is present, it will get converted back into ammonium bicarbonate and ammonium carbonate. So what will happen is that most of my things which were sticking to the side will tend to dissolve, and once I've weakened up, the stuff that was sticking by dissolving the stuff nearer to the interface, so some amount of my sodium bicarbonate will become free flowing. It will be like a slurry, and I take it out and I filter, and now I've got a clean tower once again. My tower has become clean, and now this solution, all this ammoniated brine, etc., which will become basically mostly ammonium bicarbonate, I feed that into my making tower, and I continue with my process. And as you can see, not one, I have several of these towers in series. So that's the way in which I will do this whole thing. Did you understand how the sodium bicarbonate incrustation in the tower is dealt with?
Yes, sir.
Okay, good. You'll be able to see how ingenious people are, the way they design. A lot of it is just smart thinking. And by the way, this is the temperature profile in the tower. Somewhere in the middle of the tower, you can see the temperature can go even up to 70 degrees centigrade. But by the time it comes to the bottom of the tower, it has to be cooled down. And that I do by heat exchange. And in the initial part also, we saw that the temperature is not high because the after the ammoniation of the sodium chloride brine, I've done a heat exchange and cooled it down. And this rise in temperature is all because of my reaction that took place. Okay, now let us look at typically the mass balance for the soda ash production by the Solvay process. This is given for roughly, let's say 1 ton basis, 1 ton of sodium carbonate. Now, 1 ton of sodium carbonate, actually I need 1.55 tons of sodium chloride. By the stoichiometry, if you work out like 2 NaCl plus CaCO3 giving you Na2CO3 and CaCl2, you will see that the theoretical requirement of sodium chloride comes to 1.104 ton. So you can see that we required quite a bit of extra sodium chloride. And so with respect to sodium chloride, there's nothing so great about the Solvay process. It's only got a 71% yield. You can also work out similarly the requirement of limestone, coke, etc. This is the actual requirements. The reason why people did not care much about this is because sodium chloride was a very cheap stuff. If sodium chloride was very expensive, like in Japan, all of the sodium chloride is imported into Japan, and they are very particular. They don't want to waste sodium chloride. Obviously, they have to look at ways of solving that problem. But I want to show you that it's nothing as efficient as what you might think. But then salt is not the costly part of sodium carbonate in terms of raw material cost. The costly stuff is ammonia, and it can also cause environmental pollution. So what I have to really be concerned about is my ammonia loss, and that you can see is quite low, between 1 and 1.5 kg per ton of sodium carbonate. And it is this that makes the Solvay process viable. You're doing that, as we discussed, from the limestone, basically the calcium oxide reacting with the ammonium chloride to regenerate ammonia. So that's effectively the sum and substance. It's not as if that I could not have improved the utilization of my sodium chloride. I could have. What could be some of the ways of trying to improve the conversion in this process? What might you do?
Using the extremely high quality brine solution.
Brine is what? It's about 99% pure. Unless there are inhibitors in the brine, which are thwarting the rate of the reaction, but there is no evidence of that. It would rather affect the quality of my soda ash. Suppose there was some magnesium. In presence of ammonia, it will form magnesium hydroxide. And that magnesium hydroxide will go and sit in my sodium bicarbonate. So I would have a purity problem, okay, which can happen. But it wouldn't as such affect the rate of the reaction much. It wouldn't affect the conversion. See, I could have made my Solvay tower even taller. I mean, and as the taller I make my tower, I'm giving it more residence time. The reaction between CO2 and ammonia is not an instantaneous reaction. It takes time. The reaction between ammonium carbonate and CO2 to give ammonium bicarbonate is also not an instantaneous reaction. So, if I had increased my, let's say, height of the tower, then I could have reduced my sodium chloride losses. But then, obviously, my tower building cost would have gone up, because I'd need a taller tower. So, you can see that this is how you have to do an optimization. You'll have to figure out what is the cost of my sodium chloride, what does it mean to lose 30% sodium chloride, versus if I had to build a taller tower, most people will say, let me compromise. And the place of compromise is where these things are intersecting to give you the lowest final cost. So that's how you will decide what kind of tower height you'll keep. And it can vary from country to country, as I said, depending on what is the cost of NaCl, etc. Now, similarly, whatever I've shown you are typically done at almost like ambient pressure. Maybe some amount of pressure is there. In my flue gas is pressurized, etc. But if I had increased further my, the inlet CO2 to the carbonation tower, if I had increased its pressure, naturally the CO2 concentration would go up. And if the concentration goes up, the rate of the reaction will go up. But then I would have a cost of pumping under pressure. So my pumping cost would go up because now I need a high pressure. But my sodium chloride losses would come down. Okay? Again, here I will try and select at which point I'm getting the most optimum in terms of cost. And then I'll say, this is the pressure at which I'll work, and this is the tower height at which I'll work. Many times what happens is there could be a third factor which people have not cared about much, which is that if I have to look at environmental issues. If someone says, no, 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 there are serious environmental issues which you have to look at, then, some of these things might change because there would be another dimension which I have to take care of. Is that clear? Is this figure clear?
Yes, sir.
Yes, sir.
Okay. Now I will show you another very brilliant scheme that was devised, in the 30s by Chinese chemists. It's not a huge change from the Solvay process. The main reactions that take place in the Solvay tower, essentially the same reaction takes place here. But let me tell you what are the points of departure. What they said is that let us look at some of the things which are, a bit of a hassle as far as the Solvay process is concerned. One is that I have ammonium chloride, and that ammonium chloride again has to be treated with lime to release ammonia, and then you have to put that ammonia back. So what the Chinese people said is that, look, ammonium chloride is also a very good fertilizer. So why don't we see if instead of regenerating ammonia, if I can convert it into pure ammonium chloride, which can then be just used as a fertilizer. And that's why the name which they're given is dual process. Dual means I don't have a single product focus. It is not just about sodium carbonate, but it is about soda ash and ammonium chloride. But we have seen that in the Solvay process, quite a bit of NaCl remains, which contaminates the ammonium chloride. It's not a pure ammonium chloride. If it was pure, yeah, it could have gone for agricultural application. But with sodium chloride, no, it cannot. So what they're doing is they're not changing anything as far as the carbonation tower is concerned. Everything is the same. Okay. They're again filtering or centrifuging, getting the sodium bicarbonate, which is then going into the rotary calciner. You're getting sodium carbonate. But now the ammonium chloride, what they're doing is that they're taking advantage of this particular plot. What you can see in this plot is that sodium chloride, as we said, has a very flat solubility. It's one of the really unique things about sodium chloride. Its solubility does not change with temperature. Ammonium chloride, you can see at a high temperature, okay, like in the middle of the Solvay tower, it has got a solubility far more than sodium chloride. But as I start cooling it down and I go to sub-zero temperatures, what happens is that there is a considerable difference in the solubilities of my sodium chloride and ammonium chloride, and now ammonium chloride becomes less soluble. So what Hu Debang said is that I need to do a refrigeration of this ammonium chloride filtrate which is coming out, and I take advantage of this so I can get a ammonium chloride to crystallize out, and which will be largely free of sodium chloride, and so directly it can go as a second product as a fertilizer. Okay. The second very interesting thing that they did was they took advantage of the common ion effect. Now, if I'm trying to take out ammonium chloride and I'm trying to maximize it, which are the two constituents which I should try and maximize in solution to reduce the solubility of ammonium chloride? Well, I would increase my ammonium concentration and chloride concentration. The higher those concentrations are, the more ammonium chloride will precipitate out. That's common ion effect. So what am I doing in my ammoniation tower? I'm taking sodium chloride, saturated sodium chloride. I'm taking ammonia and I'm saturating it. What they do is that ammonium chloride solution itself is going into my ammoniation tower. And into this, I am absorbing more ammonia, which I require. And because the ammonium chloride is now undersaturated in sodium chloride, I dissolve salt, solid salt, into this solution to make it into a saturated brine. So that is what I am now putting into my refrigeration tank, and I am maximizing the amount of ammonium chloride that is coming out. I've got one or two things about this slide which I still need to complete. So I'll do that tomorrow, and we'll continue with the chloralkali process after that. Okay. Is everybody clear?
Yes, sir.
Okay.